Thank you, Giovanni, for the introduction. I actually had prepared a few slides just to introduce myself, since I'm new to Imperial. But essentially, yes, I'm from Naples, Italy. I graduated as a bachelor's and master's in aerospace engineering at Federico II University there. And I really entered the world of astrodynamics through a master thesis on an orbit propagator. Subsequently, I did my PhD in aerospace engineering at the Technical University of Madrid in Spain, while I was also an early stage researcher in the Stardust Marie Curie Initial Training Network. Afterwards, I moved to the US with a postdoc, first at the University of Arizona, where I mostly worked on the dynamics of objects in the Earth-Moon system, and then with a subsequent postdoc during the last couple of years at the University of Colorado Boulder, where I mostly worked on Mars entry, descent, and landing guidance, so the topic of today. My main research areas are, well, primarily space situational awareness. That's, let's say, the research area where I started my PhD. And after that, I gradually expanded into studying guidance, navigation, and control, and also in studying applications of novel machine learning algorithms to problems in astrodynamics. As part of my work in GNC, today, essentially the talk will be about entry, descent, and landing. The results that I will talk about in the seminar are essentially from a project that I worked on at the University of Colorado Boulder. This was under a NASA grant that was given to my past advisor, Professor Jay McMahon. So I just wanted to acknowledge his contributions and those of my collaborators in Boulder, Benjamin Grace and Sheena Hume. So let's dive right in. First of all, I prepared a few slides to give an overview of the entry, descent, and landing phase for a planetary exploration mission and its challenges. So entry, descent, and landing, or EDL, is the final part of any planetary exploration mission that includes a surface component. And the phase starts at the entry interface, which for bodies with an atmosphere vaguely coincides with where the atmosphere starts. And the phase ends when the spacecraft is safely on the planetary surface. And this is quite a critical mission phase with several events that have to happen in rapid succession. As you see in the video here for Mars 2020, we might have to jettison a cruise stage, turn on the entry guidance, turn on reaction control systems, and all of this. And all of this has to happen in full autonomy because of the light time delay to Mars in particular, and also in a very uncertain environment. By definition, these are exploration missions. If we go into a little bit more details into what constitutes EDL, we start with an entry phase in which the vehicle transitions from the hyperbolic approach orbit to hypersonic atmospheric flight. Again, during the remainder of this talk, I will consider bodies within atmosphere, since we're talking the core is devoted to Mars. And during the entry phase, we have that most of the kinetic energy of the vehicle is dissipated. This is, for instance, a notional entry trajectory. You can see that the velocity goes from about 6,000 meters per second to, here it's probably around 400, and about 95% of the kinetic energy is dissipated through essentially aerodynamic drag and heating. As far as the guidance of the vehicle is concerned, we have several options have been used in past missions, of which the simplest is to just have a ballistic entry, which means that we do not apply any form of control to the vehicle during the entry. And of course, this is This is the simplest approach. However, it's not robust to perturbations, for instance, in the atmosphere. Another option that has been first used by the Mars Science Laboratory that landed the Curiosity rover in 2012 is to use a lift modulation control with a bank angle law. And essentially what this means is that we impose some kind of target for the onboard guidance, for instance, like a target range, and the vehicle has to dissipate the kinetic energy by doing S turns during the entry, while respecting this final, while trying to achieve this final range target. This is based actually on respecting trying to follow a reference trajectory during the entry that's pre-computed before the mission. A similar approach makes away with the reference trajectory, and instead we try to minimize the final error on board through a numerical predictor corrector, and this will be used, for instance, for the entry of the Orion capsule. And in this case, the bank angle law is completed on board. Regarding the descent phase, we usually have to dissipate the final kinetic energy after the entry through some form of system like supersonic parachutes or thrusters, which allow for high mass payloads. And regarding power descent in particular, the simplest form of guidance is to simply execute a gravity turn, which means that the thrust vector is oriented in the direction opposite to the velocity in order to maximize the energy that's dissipated. In this work, I will consider polynomial acceleration laws. These are polynomial in time, and in particular, the augmented Apollo power descent guidance that I will show you in a bit. There are other laws such as the universal power guidance and G-fold algorithms. Excuse me. And these are essentially algorithms that solve an optimization problem on board. And G-fold is particularly interesting because it has deterministic time to convergence and has been tested on Earth, at least, as you can see in this video here. Finally, most Mars missions also have a terminal descent phase, which, for instance, in the case of Mars 2020, we have a terrain relative navigation algorithm that avoids hazards like large boulders on the surface. This is very mission specific, and I will not go over this in detail in this talk. This was not within the scope of the project. So, if we want to enable the human exploration of Mars, we have that future missions to establish a human presence would require a 100-fold increase in landing accuracy from current capabilities, and the current capabilities essentially mean that for Mars 2020, we know we can constrain the landing site between an 8 by 7 kilometer ellipse, and we want to bring this down to 50 meters. And also we want to increase the landed mass tenfold, because rather than landing a rover that's the size of a small car, we want to actually land components for a full-fledged base for humans. This poses challenges. Well, we also have to consider challenges that are posed by the EDL phase. In particular, when we take into account the Martian atmosphere, we have that it is thick enough to generate significant heating on the entry vehicle. However, it is not thick enough to guarantee a low terminal velocity. Hence the need for instance, supersonic propulsion during the descent phase. In addition, it is impossible to exactly replicate the Martian environmental conditions on Earth, which means that the systems that we have, their performance is largely uncertain. And this is the reason essentially why no mission has landed so far at mid and high elevations over, for instance, about 2 kilometers of altitude on the surface of Mars so far. We just need more atmosphere before we hit the surface in order to give time to the systems to perform well. Of course, the Martian environment is also highly uncertain, and the variables that we're most interested in from the point of view of the atmosphere for EDL are the Martian density and the wind, which exhibit significant daily and seasonal variations. In addition, while we understand pretty well the aerodynamic performance of current entry systems, it's difficult to scale this knowledge to future systems that will exhibit higher masses. And in particular, there's a dedicated aspect that's the one of interaction of thrusters with hypersonic flows, in which, for instance, when we fire into the flow, we might have a reduction of the drag of the vehicle, which is something that we don't want since we're using that to decelerate. Therefore, we had the need for robust guidance algorithms. So under the current state of the art, a guidance algorithm generates an optimal solution under a set of simplified assumptions on board the vehicle that are actually not respecting reality for this due to these phenomena that we considered. Since the solution is approximated during the descent, we have to recompute it iteratively. However, each of these solutions along the descent will always be suboptimal, because at each time in which we recompute the solution, we are neglecting perturbations. And we can increase the frequency at which we call the guidance and use better actuators and to improve reliability. However, this is expensive and this is not a robust approach because we do not have an explicit control on the optimality of the actual solution. In this project, we tackle this problem through two main aspects. The first is the reconstruction and prediction of atmospheric quantities such as density and wind, and the other is the implementation of a stochastic power descent guidance algorithm. So I'll just give an overview of the first part on the reconstruction and prediction of atmospheric variables. Going a little bit into more detail for predictor corrector methods. Probably many of you already know how these work, but in essence, we have that in a predictor corrector, we have first a predictor step in which we propagate the current state forward in time until a final condition is met. For instance, until a certain altitude is reached or a certain energy. And once the final condition is met, we compute a measure of error. And this measure of error is used in the corrector phase to find controls that minimize it. For instance, we might do a Newton iteration if we parameterize the control law using any kind of variable. And once we found a new estimate for the control law, we run the predictor again, and hopefully we get an error that is lower. And this is repeated at each instance in which the guidance is called until a certain tolerance is reached. However, the predictor is sensitive to the dynamical model that is stored on board. Of course, for instance, if the density or winds change along the trajectory, then the actual trajectory of the vehicle will be different. Now, most state-of-the-art methods assume that we have a static exponential density profile during the predictor phase. And there are ways to improve this, for instance, by computing a scaling factor or by refining the scale height of the density profile through a Kalman filter. However, this still neglects the fact that the atmosphere of Mars is not truly exponential. So on this sketch here, the red curve is the density that is experienced along a notional entry trajectory. And if we approximate this curve with an exponential, we have that at each time we essentially approximate the curve with its tangent. And the distance between the tangent and the curve is essentially error that is being introduced in the predictor phase. So our approach is to use machine learning, in particular a recurrent neural network that's pre-trained before the mission, to estimate arbitrary density wind profiles from onboard measurements. And in particular, we use inertial measurements for now. So it's more primer on neural networks. We are in the supervised learning approach. So what we have is a data set of features X and targets Y. And for simplicity, we can assume features and targets to be just vectors that live in n or m-dimensional space. We have these samples, and we know that there is a mapping that connects features to targets. Our assumption is to approximate the mapping with f hat, where f hat is a neural network. And the neural network is essentially a sequential application of nonlinear functions, or units in machine learning terminology, to affine transformations. So, well, let me go over this sketch since it makes it a little bit clearer. We have that at the input layer, we take in the inputs to the network, which have the features, and we compute an affine transformation. So just a matrix product plus a translation. And then the output of the layer is computed by applying a nonlinear function element by element to the result of this affine transformation. And this is repeated in subsequent layers until reaching the final output layer. Now, for this to be useful, the parameters of the network which enter the affine transformations have to attain a certain value. And this value is found through training, which is a numerical optimization procedure to find a set of parameters that usually minimizes a certain measure of error or a loss function. And this is usually accomplished with gradient-based methods. So we essentially take the gradient of the loss with respect to the parameters, and we walk in the other direction until we reach a minimum. Now, in our case, our features aren't just vectors. They are a sequence of vectors because we are interested in using a sequence of measurements. And therefore, we use recurrent neural networks, which are similar to the architecture that I presented in the previous slide, with the difference being that there are so-called recurrent connections between the hidden layers. And this is essentially a mechanism of passing information from one time step to the next of a time series. Classical recurrent neural networks, however, exhibit a problem during training. The gradient of the loss function tends to either vanish or explode over long sequences. Therefore, we use a modification of this architecture that's called long short-term memory. And I won't go into too much detail into how this works, but essentially there's a few other layers in every so-called LSTM cell that prevent the gradient from going to either 0 or infinity. And the information on time steps is passed through these vectors called hidden and cell states. So essentially, we have a sequence of measurements that gets in and we get out as an output, like atmospheric quantities. So regarding the data set that we use to train the network, we took the Mars Global Reference Atmospheric Model as a truth model, and running GRAM gives us the density as a function of the altitude and position on the planetary surface, and the horizontal wind components. And we ran this model for 10,000 random samples of its parameters in order to obtain different expected density and wind profiles. So for each of the density and wind profiles, we generate an entry trajectory. We use the same initial conditions and vehicle characteristics over all samples, and we use the fully numerical predictor corrector entry guidance algorithm to provide the bank angle law, assigning a certain target range from the entry interface. And this is a plot of the reference trajectory over an elevation map of Mars. In the guidance, for now, we assume that the density profile is exponential and there is no wind, while the true dynamics, of course, consider the density of wind from the truth model. So, going a little bit into more detail regarding the features, these are normalized inertial measurements. So we have, we include in the features quantities that are typically available to the onboard guidance algorithm, such as the vehicle state in spherical coordinates, the measured acceleration, and the bank angle that was commanded at the previous time step. Therefore, we generate a sequence of measurements for each trajectory from the initial time at the entry interface until the final time at the end of entry. And we normalized these features in order to improve the network performance. And the reason why we do this is that there is research that suggests that performing this kind of normalization, it kind of, the best performance of the network is obtained when the feature set can be generated through a Gaussian distribution, a standard distribution. This is a way of kind of trying to get the feature set towards that. And also we can minimize round-off errors since the neural networks run in single precision. So the normalization is done simply by subtracting the mean of the features over the data set and dividing by the standard deviation. So nothing too complicated here. Regarding network targets, we have that the network outputs so-called pseudo-density and wind profiles along the trajectory. And by pseudo-density, we simply mean that we take the square root of the negative logarithm of the density. And the square root is there essentially to accelerate the training of the network, which we just found experimentally. And this constant B is set to 0 for Mars, but it's there for completeness. And we apply the same normalization also to the target vectors. The density wind profiles are discretized along an altitude range of interest for entry, and although the target vectors are essentially functions of the single variable, which is altitude, we still manage to capture both spatial and temporal variations. So regarding the loss function, we simply use the mean squared error in the target vector that's averaged over a mini batch, and a mini batch is just a subdivision of the entire data set that's used during a single training iteration. This is done essentially to achieve better convergence and better performance during training. And we also use a regularization penalty for the network in order to avoid it to prevent it from overfitting the targets. These are the hyperparameters and training settings, and this is a plot of the the behavior of the loss function during training, and it behaves as expected. It decreases after an initial transient, and most importantly, the loss on the training and the validation sets is of the same order of magnitude, which means that the network is generalizing well to samples that doesn't seen during training. So this is confirmed by looking at the histograms of errors in density and wind over the different sets, the training, the validation, and testing set. So we have the, first of all, from this box we can see that the errors both in density and wind are pretty low, under 1% for density and 5% for the wind. And these are root mean square error over the full range of altitude computed over each sample. Also, yes, the errors are consistent across the different sets, which means that the network is able to generalize well. If we look at what happens as a function of altitude, things get a little bit more interesting. We have that the while the density error stays pretty low along the entire altitude range, we see that the error in the reconstructive winds explodes after about 55 kilometer altitude. And the reason why this is because at those altitudes, there's really not enough dynamic pressure because of the low density. So this means that different samples in the data set give the same measurements in that altitude range, and therefore the network is not able to discern between different wind profiles among the samples. Now, this is all well and good. We have that during a single trajectory, what we've done so far is to take measurements each time that the guidance is called. And once the trajectory is completed, we feed this sequence of measurements to the LSTM network, and we obtain density and wind profiles. And this is useful for reconstruction of the atmospheric quantities a posteriori, let's say after the entry. However, for this to be applicable to improve the guidance algorithm, we want to feed the network partial sequences during the entire trajectory. And we're currently working on this. We found that by using the same algorithm to perform intermediate predictions, meanwhile, during the entry trajectory, we have that the errors can be quite large and actually comparable to those of a simple exponential model. And the reason why this happens is that the target vectors that are used in the loss functions are obtained essentially only at the final time. Therefore, I'm currently working on the implementation of a custom loss layer in which we also average the loss over all past time steps. And also, if this is not sufficient, we might also employ algorithms that are time invariant, such as convolutional recurrent neural networks. Now, on the second part of the project, which is stochastic powered guidance. First of all, I'd like to introduce the power descent guidance problem. We have that in the power descent guidance, we assume to know the current position and velocity at time t, and we want to bring this state to a target state R star and V star at a certain time tf under these equations for the dynamics. These can be done by using the so-called augmented Apollo power descent guidance, and this is an analytical law that has been proposed in a recent paper. I forgot to put the reference here, but I can provide it after the talk. This law for the thrust acceleration is a first or second order polynomial in time, depending on the choice of this gain kr, and it is a fixed final time law, so tf is a constant and it's assigned. As you can see, in the dynamics, there are no aerodynamic accelerations that are considered, and also there is no provision for introducing thrust limits or lag from actuators and other effects. Therefore, this is subject to dynamical uncertainty. We carried out an uncertainty analysis for this particular guidance law, in which we used uncertainties in initial conditions, navigation. So we assume that the state vector used by the guidance does not correspond to the true state, but it's affected by stochastic errors, and also uncertainty in the thruster performance. We assume that the initial state is Gaussian in Cartesian coordinates in a Mars fixed frame, and we assign a desired target that's on the surface 7 kilometers downrange from the start of our descent. For the initial conditions uncertainty and for the navigation uncertainty, we assume that the initial state and the navigation state are both random variables that have a spherical, that are represented by, that have a spherical uncertainty. This means that their covariance is diagonal. It means that the contours of probability where they can be located are spherical. This is just done for simplicity. The thrust uncertainty is modeled as a random scale factor. So for each trajectory that we examine, we scale the actual thrust that is used by the vehicle through a single scale factor that's distributed as a Gaussian. As far as navigation errors go, yes, we feed to the guidance a navigation vector that's equal to the true state vector plus an error delta x, and the navigation error is devised in order to simulate a correctly tuned navigation filter. In particular, we have that for each trajectory we sample a vector c, which is zero mean, and it's drawn from a standard Gaussian, and we scale this through the Cholesky decomposition of the covariance of the navigation covariance, and we just assumed an exponentially decreasing law for the covariance, since this is what we see usually in a navigation filter. All this means that the navigation errors are fixed in direction, and their magnitude decreases exponentially during the descent. We use these uncertainties in a Monte Carlo campaign with 5,000 samples, of which almost 1.4% exhaust the propellant, and 75% land with a final velocity error that's greater than 2.5 meters per second, and this essentially means that we had a hard landing and a failure. And this just gives us an idea of the kind of uncertainties that we can deal with in the during EDL. If we look at the distributions of position and velocity errors on the surface, we have these panels here. This panel is just a zoom in of the entire distribution of position errors. The most interesting thing to note here is that the mean of the final position and velocity errors is not zero, which means that these distributions, although it might be kind of hard to see from these plots, these exhibit a bias with respect to the intended landing target. And we also have that the standard deviations are also pretty high, but this could be expected since we introduced pretty large uncertainties. The fact that we introduced a bias in the final landing distribution is actually expected by looking at what happens in nonlinear systems, as is our dynamical system in this instance. In fact, we have that if we start from initial conditions that are a random variable and propagate its mean forward, we will arrive at a certain value at the final time that's in general different from the mean of the propagated state uncertainty at the final time. So this means if we propagate the mean of the initial conditions forward, we get to a certain value, and if we propagate the PDF forward and then compute its mean, then we will obtain something different. Based on this observation, we want to devise a stochastic retargeting algorithm in which, rather than minimizing the nominal landing error that's based on the propagated mean, it's thought to minimize the mean of the landing error in a stochastic sense. And the PDF is the navigation PDF in our case is propagated through an uncentered transform under the control dynamics, so in the presence of thrust. And finally, we use the final mean error to apply a correction to the nominal guidance target in order to minimize the error in a stochastic sense. Just to give a few details about the uncentered transform, this is essentially a mathematical method to propagate a Gaussian PDF through a nonlinear transformation. And this essentially works in 3 steps. The first is, first of all, we assume that we have a random variable x with a certain mean and covariance. And based on this, we sample the neighborhood of the mean, obtaining 2n+1, where n is the dimension of x, 2n+1 deterministic sigma points. So these are the formulas to compute them. And we essentially sample along the eigenvectors of the covariance matrix of x. We propagate each of the sigma points forward through the nonlinear transformation, and then we reconstruct the mean and covariance of the final Gaussian PDF as a linear combination of the transformed sigma points. We use the uncentered transform in a preliminary test of the retargeting algorithm, in which we propagate an entire bundle of initial conditions, an entire set of initial conditions under uncertainty, until hitting the surface, and the control history is assumed to be the same as the mean for all sigma points, and we compare this with a Monte Carlo. And we found that if we correct the target of the guidance law, we can significantly reduce the position error, reduce it by an order of magnitude, while so far the velocity error remains unchanged. This is likely due to the fact that we neglected the impact of the terminal descent so far. We're also validating using the uncentered transform to propagate the navigation PDF. The navigation state vector is as shown earlier, so it's a Gaussian random variable, and the navigation PDF is propagated under the control dynamics using the mean control history for all of the sigma points. And finally, we marginalize the final ellipsoid of uncertainty to obtain a landing ellipse, and we compare this to another Monte Carlo. And we have the final covariance obtained with the uncentered transform reflects well the one that is expected from the Monte Carlo, but there is a discrepancy in the position of the means that I am currently working on. Once the uncentered transform for the propagation of the navigation uncertainty is validated, we can perform an iterative retargeting scheme. Essentially, this works by fixing sometimes during descent. For instance, every 5 guidance calls, we perform an uncertain transform of the current uncertainty until reaching the ground. And then we correct the target for the main guidance algorithm in order to minimize the final mean landing error. And this essentially prevents the mean of the navigation uncertainty from departing from the nominal trajectory that we assigned. So this is a closing slide for my talk. Just to summarize the main points that I've covered so far. First of all, the entry, descent, and landing phase of the Mars exploration mission is affected by significant uncertainties, of which the most relevant are the uncertainty in the atmospheric quantities, and which are also highly variable, and also the modeling of hypersonic and aerodynamics in the presence of thrust. We propose a recurrent neural network for the reconstruction of atmospheric quantities starting from inertial measurements, which obtains pretty low errors both in replacing density and wind. And we're currently working on extending this approach to online predictions to enhance the guidance. And finally, we carried out an uncertainty analysis for power descent. We validated the propagation of the uncertainty in initial conditions through uncertainty transform, and also working on the validation of the propagation of the navigation uncertainty. So this is all for my talk. Thank you for your attention, and I'm happy to take any questions.